Good morning. This chapter we'll be seeing about heat treatment of steels. Generally, it is called as thermal processing of metals. So, there exists a phenomenon that we all know, which occur in metals and alloys at elevated temperatures. For example, recrystallization and the decomposition of austenite. These are effective in altering the mechanical characteristics when appropriate heat treatments or thermal processes are employed. In fact, the use of heat treatment on commercial alloys is an exceedingly common practice. Therefore, we consider next the details of some of these processes, including annealing procedures, the heat treating of steels, and precipitation hardening. So, annealing process refers to a heat treatment in which a material is exposed to an elevated temperature for an extended time period and then slowly cooled. Ordinarily, annealing is carried out to relieve stresses, increase softness, that is ductility, and toughness, and also it is used for producing a specific microstructure. A variety of annealing heat treatments are possible. They are characterized by the changes that are induced, which many times are microstructural and are responsible for the alteration of mechanical properties. Any annealing process consists of three stages. One is heating to the desired temperature, holding or soaking at that temperature, and cooling. This is an important process parameter in these procedures. During heating and cooling, temperature gradient exists between the outside and inside portion of the piece, that is the workpiece. Their magnitude depends on the size and geometry of the piece. If the rate of temperature changes too great, temperature gradient and internal stresses may be induced that may lead to warping or even cracking. Also, the actual annealing time must be long enough to allow for any necessary transformation reactions. Annealing temperature is also an important consideration. Annealing may be accelerated by increasing the temperature because diffusional processes are normally involved. There is another class of annealing process which is called as process annealing. So, process annealing is a heat treatment that is used to negate the effects of cold work, that is, to soften and increase the ductility of a previously strain hardened metal. It is commonly utilized during fabrication procedures that require extensive plastic deformation to allow a continuation of deformation without fracture or excessive energy consumption. Recovery and recrystallization processes are allowed to occur. Ordinarily, a fine-grained microstructure is desired, and therefore the heat treatment is terminated before the appreciable grain growth has occurred. Surface oxidation or scaling may be prevented or minimized by annealing at a relatively low temperature, but it should be above the recrystallization temperature. Or in some cases, a non-oxidizing atmosphere is provided to reduce the oxidation. Say for example, a furnace with vacuum, a furnace that can be supplied with inert gases such as argon, nitrogen, CO2, etc. The third category of annealing is called as stress relief annealing. So this stress relief annealing is used when internal residual stresses may develop in metal pieces. These stresses are developed in response to the following conditions. One is the plastic deformation process such as machining or grinding, or non-uniform cooling of a piece that was processed or fabricated at an elevated temperature such as welding or casting, etc., and a phase transformation that is induced upon cooling wherein parent and product phases have different densities. Distortion and warpage may result if these residual stresses are not removed. They may be eliminated by a stress relief annealing heat treatment, in which the piece is heated to a recommended temperature, held there long enough to attain a uniform temperature, and finally cooled to room temperature in air. The annealing process or the annealing temperature is ordinarily a relatively low one, such that the effects resulted from the cold working or any other heat treatment process that are not affected. There are several different annealing procedures that are employed to enhance the properties of steel alloys. However, before they are discussed, some content related to the labeling of phase boundaries is necessary. You can see the figure above, which shows the portion of the iron carbon phase diagram in the vicinity of the eutectoid. The horizontal line at the eutectoid temperature, conveniently labeled A1, is termed the lower critical temperature, below which, under equilibrium condition, all austenite will have transformed into ferrite and cementite phases. The phase boundaries denoted as A3 and ACN represent the upper critical temperature lines for hypoeutectoid and hypereutectoid steels. For temperatures and compositions above the boundaries, only the austenite phase will prevail. Alloying elements will shift the eutectoid and the position of these phase boundaries. One of the processes which commonly used for ferrous alloys are normalizing. Steels that have been plastically deformed, for example a rolling operation, consists of grains of perlite and most likely proeutectoid phase, which are irregularly shaped and relatively large, but vary substantially in size. An annealing heat treatment called normalizing is used to refine the grains, that is, to decrease the average grain size and produce a more uniform and desirable size distribution. Fine grained perlitic steels are tougher than coarse grained ones. Normalizing is accomplished by heating at least 55 degrees Celsius above the upper critical temperature, that is the above A3, for compositions less than the eutectoid, that is 0.76 weight percentage of carbon, and above ACM for compositions greater than the eutectoid, or that is represented in the figure. After sufficient time has been allowed for the alloy to completely transform to austenite, a procedure termed austenizing, the treatment is terminated by cooling in air. A normalizing cooling curve is superimposed on the continuous cooling transformation diagram. Next process that is commonly used is full annealing. A heat treatment known as full annealing is often utilized in low and medium carbon steels that will be machined or will experience extensive plastic deformation during a forming process. In general, the alloy is treated by heating to a temperature of about 50 degrees Celsius above the A3 line to form austenite. For compositions less than the eutectoid, or for compositions in excess of the eutectoid 50 degree above the A1 line, to form austenite and Fe3 phases. The alloy in the furnace is cooled, that is, the heat treating furnace is turned off and both furnace and the steel cool to room temperature at the same rate, which takes several hours. The microstructural product of this anneal is coarse perlite, in addition to any proeutectoid phase that is relatively soft and ductile. The full anneal cooling procedure is time consuming. However, a microstructure having small grains and a uniform grain structure results. Spherodizing. Medium and high carbon steels having a microstructure containing even coarse perlite may still be too hard to conveniently machine or plastically deform. These steels, and in fact any steel, may be heat treated or annealed to develop the spherodite Structure. Spheroidized steels have a maximum softness and ductility and are easily machined or deformed. The spheroidizing heat treatment, during which there is a coalescence of Fe3C to form the spheroid particles, can take place by several methods. Heating the alloy at a temperature just below the eutectoid line, that is line A1 in the figure, or at about 700 degrees Celsius in the alpha plus Fe3C region of the phase diagram. If the precursor microstructure contains perlite, spheroidizing times will ordinarily range between 15 to 25 hours. Heating to a temperature just above the eutectoid temperature and then either cooling very slowly in the furnace or holding at a temperature just below the eutectoid temperature. Heating and cooling alternatively within plus or minus 50 degrees Celsius of the A1 line as shown in the figure. To some degree, the rate at which spheroidite forms depends on prior microstructure. For example, it is slowest for perlite and the finer the perlite, the more rapid the rate. Also, prior cold work increases the spheroidizing reaction rate. Still, other annealing treatments are possible. For example, glasses are annealed to remove residual internal stresses that render the material excessively weak. In addition, microstructural alteration and the attendant modification of mechanical properties of cast irons result from what are in a sense annealing treatments. With this, we come to the close of annealing procedure for steels. Thank you.